Okay, lecture number 5, heat engines and refrigeration. All right, so if we review the first law of thermodynamics, basically it gives us some basic underlining information in terms of it's a statement of the conservation of energy. That's a very important concept. We know, obviously, internal energy is equal to Q plus W, but if you really analyze that, the entire equation, it just kind of tells us that all the energy that you put into a system is going to equal the energy that the system essentially contains. All about conservation. All right, so a change in internal energy obviously can result by an energy transfer of heat, by work, or by both. All right, so a few missing pieces that we have for this first law. All right, so only certain types of energy conversion and energy transfer processes actually take place in nature. All right, and so that's kind of setting the groundwork for that. There's processes that that we as humans actually have taken upon ourselves to go ahead and kind of work against nature, if you will, to go ahead and do processes that are not natural. All right, so the first law makes no distinction between processes that occur spontaneously and those that do not. All right, so if we think about this, one example is it's impossible to design a device that just takes in energy and converts it all to another form of energy without adding any extra energy to do that. All right, so you can't just convert heat energy into work basically without adding some extra energy into the system to go ahead and do that. Right? Think about conversion from the sun's radiation to electrical energy. There's some loss going on there. All right, if you think from mechanical work to electrical energy, there's always going to be some kind of loss associated with that, and that's what we're really going to get into right now. Okay, so the second law of thermodynamics is what we're going to get into right now. All right, basically all it does is it just establishes which processes do and do not occur. All right, so when we say processes, remember we always have this graph. All right, pressure here, volume here. Maybe we went from some initial position to some final position over here. All right, and if we do a curve, or if it was a constant pressure, constant volume, all right, we can understand that we have a natural direction for any process like that, right? But some processes, all right, they can't occur in that particular direction just because they might violate some law of thermodynamics, right? So we observe these motion from some initial to final, or this process, I should say, from initial to final, as occurring in only one direction. All right, we don't say that they occur in both directions at the same time. All right, and so the second law of thermodynamics is really going to tell us all about what directionality that process actually follows. All right, so what we have here is an irreversible process. As you can imagine, is a process that is going to occur naturally, but only in one direction. All right, so if it's a constant pressure process, constant volume process, isothermal, adiabatic, all right, it goes from some initial condition to some final condition in one direction only. It can't go backwards along that line, basically. So no irreversible process has been observed to actually run backwards. All right, and so this is typical of heat engines, is what we're going to get into right now, because heat engines are not, or any engine that we know of is not 100% efficient, meaning that it doesn't take all of its fuel or energy they would put into the engine and just completely turn it into work, the same amount of joules of work for that. So we have a limited efficiency for this because of the second law of thermodynamics, which essentially tells us that irreversible processes, all right, can only go in one direction. All right. Okay, so what is a heat engine? Heat engine is a device, you probably already know, that takes in energy by heat, all right, operates in a cyclical process because we want this to keep on happening, and expels a fraction of the energy into work, all right? But it's only a fraction. Okay, so what's an example of this? Electrical power plant. It uses fuel to produce steam, all right? And then that steam can be kind of funneled into a pressurized system to go ahead and create a lot of force on a turbine to go ahead and get that turbine to turn, and then we get electrical generation from just turning the turbine. But we need a significant amount of force, and we're not going to get people to turn this turbine because that would be inhumane, but we would want to actually allow processes. All right, so basically we put a lot of energy to produce the steam, basically boiling water if you think about it. All right, or we could use dams, hydroelectric dams that can put a lot of force into a certain cross-sectional area, and we could funnel that into a turbine. Right, whatever we do, we're trying to use this mechanical work, all right, we're trying to get mechanical work out of the system by putting heat into the system. Okay, another example is the pistons in an automobile, right? We're actually putting in heat energy to go ahead and get mechanical work out of that system, right? But we understand for any automobile, any car, we have this exhaust that runs on gas, I should say. We have an exhaust aspect, right? And that would be that's a fraction of that energy that we put into it is not only work, but it's also heat that gets expelled into the environment, right? So heat engines are going to carry some kind of working substance. All right, this could be air or it can be liquid. Typically, it's a gas or a liquid. All right, that can be easily carried through the process that carries that heat with it. All right, either to be expelled or to be used within the engine itself. All right, so here is your basic heat engine. This is just a general picture that we can kind of take a look at everything that's happening here. All right, so we can understand what are we trying to get out of this heat engine. We want as much work as possible. All right, so we have a hot reservoir. All right, in an automobile, this essentially is like a spark plug that's igniting gasoline. So it creates a lot of heat to go ahead and put into your engine. All right, and what we get out is work, and then we also have expelled heat, which is the QC. All right. The only difference between QH and QC, obviously, is the magnitudes of each other, but also that QH is connected to some kind of hot temperature reservoir. The QC is connected to a low temperature reservoir, this TC right there. All right. So this is a cyclical process, and what's nice about cyclical processes is that for the first law of thermodynamics, we could say the internal energy change is equal to zero, right? Because it comes back exactly to the same spot that it started. All right, so if this is initial, this is final, it came right back to where it started, and that would mean the internal energy is zero. All right, so let's just think magnitudes here. That just means the work done on the engine is a negative amount of work, right? And also depends upon if we're expanding, or moving a piston in a certain direction. This doesn't have to be a piston, it could be another example of a heat engine here, but basically the bottom line, if you just think magnitudes, since the delta E internal is going to be zero, well then you know the amount of heat that you put into the system, all right? And I should say not just put in, but actually absorbed by the engine, because there's also going to be heat that's going to be expelled. So the heat that you put into the engine is going to equal the amount of work that the engine can produce, basically. All right? So this really said a different way is Q, if I can draw it correctly. All right, we could say QH minus QC, because one is bigger than the other, is going to equal the work of the engine. All right, so it's a very simple statement that we can make. All right, that QH minus, this should be a QC, all right, is equal to the work of the engine. And QH minus QC, that's just the net energy, heat energy that the engine absorbs. All right, so let's put this in terms of efficiency, because that's always an important part of an engine. All right, this is the ratio of the net work done by the engine during one cycle to the energy input at the higher temperature. All right, so just think about it. A heat engine, we are going to go ahead and put in QH, right, into the heat engine. All right, what we want to get out of it is the work. All right, so obviously we would want 100% efficiency, but that's just not going to be possible. All right, but we want to get as much work out of it as possible. Okay, and we already said that the work of the engine is QH minus QC, so you can also divide that by QH for another version of efficiency. And then since QH and QH are, when you divide them into each other, just become 1, you have 1 minus QC over QH. All right, so that's just a few ways to represent efficiency of a heat engine. All right, you can think of it as the efficiency as the ratio of what you gain to what you give. All right, so you give QH, it's on the bottom, what you gain is the work. All right, now in practice, all heat engines expel only a fraction of the input energy, only a fraction, all right? Only a fraction that actually is turned into mechanical work. Okay, so therefore, efficiency is always going to be less than 100%, all right? In order to have efficiency of 100%, that QC, that just basically cannot be any exhaust at all, right? So if we think about that, QC has to be 0, right, in order for there to be 100% efficiency. And that's not possible for any heat engine that we know of. All right, so a gas engine, your typical gas operated car is going to be a 20% efficiency. A diesel engine has higher efficiency, 37.5%. All right, so even the engines that we use on a regular basis don't have anything close to 100% efficiency. All right, so it's impossible to construct a heat engine that produces no effect other than input of energy by heat from a reservoir and the performance of an equal amount of work. Right? So basically, this is what we call the Kelvin-Planck form for the second law, just meaning that we can't have QC equals 0, basically. You can't have QH equaling your work that the engine comes out of, or that comes out of the engine. Right? You can't have QC equaling 0 either. Right? There's always a QC, a heat energy that actually gets expelled to the environment for any heat engine. So once again, the efficiency of a heat engine cannot be 100%. Right? And this once again is the impossible heat engine. And why is it impossible? Because there's no QC here, which just means that you put heat energy into the engine and you get all that heat energy turned into the work of the engine. Right? So that's impossible to construct such an engine like that. Let's do an example that kind of basically very simple, that just calculates the efficiency of an engine given the QH and the QC, not for the impossible engine, but for some real type of engine. Okay, for this example, we have an engine that's going to transfer 2,000 joules of energy from a hot reservoir during a cycle and transfers 1.5 times 10 to the third joules, so 1,500 joules as exhaust to a cold reservoir. So I think right off the bat, you can understand that QH is equal to 2,000 joules, right? QC, because it's a cold reservoir, is going to be that 1,500 joules, right? So for part A, we can go ahead and use the efficiency equation for an engine. Right? Efficiency is equal to 1 minus QC divided by QH. And we could just use absolute values in this case. And we typically are just going to use the positive aspects of the heat. So it's just a good rule of thumb. Just use the absolute values. All right, we just plug in 1 minus 1,500 is on the top, QC, 2,000 is on the bottom. The joules will cancel out, and we're left with 0.25, which is also the same thing as 25%. So this engine has 25% efficiency. All right, part B is just finding the work the engine does in one cycle. All right, and so hopefully you remember the equation that work of the engine is equal to QH minus the QC, right? Because the engine's going to take in the work, and it's also going to take in the, as we can imagine, it's going to go ahead and be related back to the exhaust that we're going to exhaust out to the cold, right? So we have the work that the engine does in terms of the output, all right? So if we kind of remember what we have here in terms of hot and cold reservoirs, all right? So we're going to put heat energy into it, all right? But what we get out from any engine, any good engine, is going to be that work energy, and we also get the cold exhaust that we get, all right? So makes a lot of sense. Since QH is equal to W plus the QC, then we get this same equation right here. So all we need to do is plug in QH is 2,000, and then QC is 1,500, and we're just left with 500 joules for the overall work that the engine does in one cycle. All right, now let's get into heat pumps, right, which can also be called refrigerators, depending upon which kind of mode you operate a heat pump. All right, so basically heat pumps are just heat engines that are run in reverse, right? And so if you can imagine that, if a heat engine took in, QH, right, and gave you QC, that's kind of a natural kind of thing, right? QH, is at a high temperature, QC is at a lower temperature. That's just like a natural way of doing things, but you also do get work out of the system, all right? So that's fine. But for a heat pump, or even think about a refrigerator, essentially what we're trying to do is try to reverse that, right? You're trying to actually input QC to get QH out of your heat pump in that case, all right? But you're kind of putting QC into the heat pump, and you're putting work into the heat pump to go ahead and get QH out of it. And you'll see a picture of this in just a little bit, all right? But this right here is just not a natural direction for energy transfer, because you're trying to get QH from QC, and that doesn't, heat doesn't like to flow that way, or doesn't flow that way, I should say, all right? Unless you put work into the system to go ahead and force the system, all right? So energy must be put into a device to go ahead and get that to happen, that heat engine basically running in reverse, which is what we call a heat pump, all right? So also called a refrigerator as well. So a refrigerator is a heat pump. An air conditioner can also be considered a heat pump as well, all right? You just think about an air conditioning system, all right? It's typically connected to some outside environment where the outside environment is hot, and what you're trying to do is get cold air into an area that is typically hot, right? And that's not a natural process, okay? So we have to put work. That's what the air conditioner does. It takes electrical energy to go ahead and put mechanical work into allowing that process to happen. All right, so here's the heat pump process, all right? This is the exact opposite of a heat engine. You see QC going into the heat pump, work going into the heat pump, and what you get out of it is QH. Right? Now, the question to ask yourself is, how does this even look like a refrigerator? Right? Well, let's think about it. For a refrigerator, you know that you're trying to extract energy out of your food, basically. All right? You get energy out of your food. You know that your refrigerator is plugged into the electrical outlet, so work is being put into the system, and what you get out of your refrigerator is this hot heat, QH, right? And so there's some kind of exhaust in your refrigerator. Typically it's on the bottom in front of it, kind of shooting out into the kitchen, which essentially makes your kitchen a little bit warmer than most rooms in the house, all right? But that's the sacrifice you pay to go ahead and keep all your food nice and refrigerated, all right? And obviously even more QH gets expelled when have your freezer on at a high level, all right? So energy is extracted from the cold reservoir, right? Typically the inner, the volume of a refrigerator, right? And energy is transferred to the hot reservoir, QH, all right? But we also have to put W into the system to allow that to happen. All right. So here's what we call the second law of thermodynamics, but in a different form, the Clausius form, right, which essentially just says it's impossible to construct a cyclical machine whose sole effect is to transfer energy continuously by heat from one object to another object at a higher temperature without the input of energy by work, right? Remember from the very first lecture that we had two objects touching each other, object A, object B. One was hot, one was cold, all right? We know that energy was going to go ahead and transfer this way. It does not go the other way, all right? That just cannot happen, okay? So energy does not transfer spontaneously by heat from a cold object to a hot object, as I just mentioned right there. In order for that to happen, you need to put work into the system, all right? It cannot happen any other way. So this is the impossible heat pump, all right, where you don't put any work into it, but you just know it's impossible because QC does not turn into QH, we'll call it QC right here, but you can't get QC coming out of the heat pump when you also put QC into the heat pump, all right? Because once again, cold or energy doesn't go that way. It doesn't go from cold to hot, right? It goes from hot to cold, okay? So this is impossible, right? You can't expel the same amount of energy as you put into it in this format. All right, so there's something called the effectiveness of a heat pump, and actually we call that the coefficient of performance, the COP. All right, so it's like the thermal efficiency for a heat engine, all right, but we call it the COP or the COP. So what is the COP? COP, actually, we got to be careful. There's two modes that you can use. COP can be used in the cooling mode or then in the heating mode. Right? So in the cooling mode, which essentially is a refrigerator, all right, or an air conditioner, what you're doing is gaining energy that's removed from a cold temperature reservoir. Right? How your refrigerator works, if it's a good refrigerator, it means that it can extract a lot of energy from the cold reservoir to keep your food warm, to keep your food cold. Right? But we also have to keep track of how much work we put into to the heat pump, to go ahead and allow that to happen, all right? So we typically have a high QC value compared to W, all right? These values of COP are typically around 5 to 6, all right? And we want them to be as high as possible because we want a good amount of QC for the amount of work that we actually put into it. All right, the next mode is called the heating mode. That's the COP, and I'll put a little H right there just to make sure that you're careful, all right? Because you actually want to heat something up. You're trying to expel, not extract in this case. You're trying to expel heat energy into a certain environment and typically to heat something up, all right? So, this is not a heat engine. A heat engine is all about getting work out of the engine. This is a heat pump, but this heat pump, really what you're looking at here is to get heat into some environment, all right, to go ahead and warm things up typically. All right, so what are we looking at here? We're looking at the QH, and we're also looking at the work that we put into it. We're just dividing QH by work. And you notice that we always have an absolute value system here to make things a lot easier for us. So COP and efficiency will always be a positive value, okay? So the energy transferred at the higher temperature divided by the work done by the heat pump, that is the COP. All right, so QH is typically higher than W, right? They're always greater than 1, right? I'm sorry, let me take that back. It's not always greater than 1. It is possible for them to be less than 1 in terms of the COP value for the heating mode, all right? So QH can be less than work, but that just depends upon how much energy you're willing to put into the system or how efficient, obviously, your system is. Okay? So heat pumps that extract energy from the air are most satisfactory in moderate climates. All right. So if we think about, when is heating mode actually used? Well, let's think about a heater. Okay. I'm sure you've seen heaters before. There's radiating heaters that just heat up some coils, and then you just have a hot, basically, object in your room that's just going to heat up the room. Not really the most efficient use of energy, but imagine you have a heater that's attached to some coils, basically tubes that are in the ground. If you have these tubes in the ground and these tubes are all connected to each other, right? And they're deep in the ground. You can imagine you can run fluid through those tubes, and that fluid there's work being done by this heater right here to go ahead and push the fluid through, all right? And so if you get deep enough, all right, you can actually have warm temperatures down there, right? Let's say it's relatively cold outside, but you actually put these coils really, really, really low. They can go ahead and transfer the heat that's down in the earth, all right? And so basically transfer it through this entire system to go ahead and get pumped. And then that heat energy can then be delivered to the inside of some house, basically. Imagine this is like in the window or it's in the wall, basically. You can actually expel that heat energy into the room, all right, basically through the use of fans, all right? So this is a pretty common system, right? But you can imagine that it has to be done only in moderate climates, right, where you could actually get heat out of the ground, and it's not very difficult for you to do that, right? But still, we have moderate climates here in California, all right? We do have the use of heaters that actually use this process here, right? In colder environments, there's just not enough energy in the ground to go ahead and get this done, all right? So that would be an example of a heat pump being used in heating mode. One other quick example is, one of my friends has some kind of solar heat system for his pool, right? So imagine if there's a pool over here. Sorry, it's kind of crude here, but there's a pool, all right? And there's some tubes once again, and those tubes are being hit by the sun, all right? So once again, even though it's cold outside, if there's a clear day, the sun can actually hit those tubes, and there's fluid being pumped, basically just water that's being pumped through these tubes right here. And basically it just pumps warmer water into the pool to go ahead and heat it up, right? But once again, you need to put work into that system to go ahead and allow that to happen. So, so if it's cold outside, you gotta, this really only works if you can actually have sun exposure, right? Even though if it is cold, it's still going to be able to heat up the pool because that sun can actually heat up this moving water. All right, so got a couple examples that are being used widely today. All right, let's take a look at an example using freezing water, right? Related back to a refrigerator that's going to try to freeze some water, and looking at the COP values and the heat that's involved with that. Okay, so we have a refrigerator. It has a COP of 5. So we'll just kind of get these ready to go. Alright, so COP of 5. Alright, the refrigerator is running. The power input is 500 watts. Alright, so we could say that the power, gotta be careful about that. Power is equal to 500 watts. Alright, a sample of water has a mass, so I'll say mass is equal to, let's convert that already, so 5.5 kilograms is 500 grams, and it has a temperature of, we could call it T initial, is going to be 20 degrees Celsius. Alright, so we're going to end up at T final is equal to 0 degrees Celsius, but we're also going to be all that water turned into ice. So it's very important to make sure we understand what's happening there. Also, we're talking about a refrigerator, so we know that we have to put work into the system. We also have to put a cold heat into the system, right? And we get an exhaust of hot heat, right? A higher heat in that case, right? Because basically the refrigerator is going to work off of the energy that's extracted from the internal aspect of the refrigerator, okay? So we can go back to what we've already learned, is that this is a refrigerator, so this means COP is in cooling mode, all right? And so this is going to equal whatever your QC is divided by work, all right? And don't forget it's an absolute value, but we're going to be dealing with positive values anyways. All right, so if we go back and take a look at power, power we know is energy over time. And this is the energy that we're talking about is the work that we're putting into the system. All right, so this is how we're going to try to relate this power value back to what we have here. So work divided by a change of time. All right, and we could say that the change of time is equal to work divided by power. Right? And so if we're trying to find how long it takes in order for this process to happen, essentially we're trying to find delta t. Right? So what we can go ahead and further do, right, is that since we know that W is equal to, from this equation, W is equal to the work is equal to QC divided by COP, well, we can plug that right into this equation here. Right. So we have that the change of time, the time, is equal to your cold heat divided by power divided by the COP. Alright, so we have a few things to plug in, but we also need the QC, the energy that got extracted. And don't forget, we are lowering the temperature to 0 degrees Celsius, and we're also turning it into ice. So we have MCAT, mass of the water, times the specific heat of water, times the change of temperature, plus the mass of the water, times the latent heat of fusion, since it's water turning into ice in that case. All right, I'm using positive signs because we know this is all absolute value, right? So we're not subtracting anything, no negatives involved. And we have P and COP already, so 500 on the bottom, COP is 5. All right, so let's plug everything in. Mass is 0.5. The CW is 4186. The delta T is 20. All right. And we know overall this is going to be a negative 20 because we're reducing temperatures, but since we're using absolute value, we're just adding all this stuff up. All right. And plus the mass of the water, which is 0.5 again, and latent heat of fusion is 3.33 times 10 to the 5th. Right? So all of this is over the 500 times 5. All right, and so if you solve this, you just get seconds in return, and you get 83.3 seconds. All right, so not too bad. Just got to keep in mind, when we're talking about extracting heat out of the system, you most definitely have to keep in mind what equations are we going to have to involve. If we have a phase change, latent heat is involved. If it's just a temperature change, well then MCAT is involved. All right, let's go back to the engine. All right, and we have Sadie Carnot right here, who is an engineer, and basically he was able to show the quantitative nature between work and heat. All right, the relationship between work and heat in an engine, basically. Okay, so his contributions really revolutionized the steam engine, basically, and understanding what limitations we can actually have for the steam engines and how efficient a steam engine can actually be, depending upon, or was based upon his work, reflections on motive power of heat. All right, so what is the Carnot engine? All right, a Carnot engine doesn't really exist. It's actually a theoretical engine that was developed by Carnot. All right, so but basically the theoretical engine sets the upper limit for all engines. All right, the upper limit for all engines is not 100%. We can never get to 100%. All right, but his heat engine, all right, if it was operating in an ideal reversible cycle between two reservoirs, so obviously one's hot and one's cold, all right, this is the most efficient engine that we could possibly get, all right, using the Carnot cycle. So basically it sets the upper limit of efficiency for all engines that we can ever think about. All right, so what did Carnot come up with? All right, he said that no real heat engine operating between two energy reservoirs can be more efficient than his engine, all right, operating between the same two reservoirs. All other engines are just going to be less efficient, all right, because they do not operate through a reversible cycle. The reversible cycle is the important aspect here, all right. Trying to have a process that just reverses itself without adding any extra energy is not really feasible. All right, you can understand when you have your automobile, you always have to use gas, burn it, and then get that gasoline out of there. All right, so that's not a reversible cycle, but it's close, but it's not reversible. Okay, so if we can understand that all the systems that we can really think about, they're not reversible. They use kind of get from one initial condition to a final condition, and then we just start over basically. But it's not a reversible cycle, all right? But the Carnot cycle is reversible, so it does put that upper limit on any particular engine, all right? The efficiency of a real engine is further reduced by any other energy loss, and that could be through friction, conduction. We didn't insulate our engine very well. Right, so that just tells you that the efficiency will always be less, right, than what we want it to be because of these things that are losing energy for us, right? But Carnot came up with a system that we can't take into account friction or energy, or assuming that everything is perfectly insulated. He set the upper limit. So here's an overview of his cycle, all right. And basically, we're going to go through these things individually here, starting with A and then ending at D, and then going back to A. But the main thing I need you guys to think about is how we start. We start with isothermal expansion, all right? And you notice that basically we're adding heat energy into it. Next step is going to adiabatic expansion, which essentially means that the temperature is increasing, but obviously Q is still equal to 0, right? And you notice that there's no energy reservoir anymore. There's an insulating plate right there. The next step is back to isothermal, but it's a compression because we put this cold reservoir touching our engine right here, touching the piston basically, all right? And so that doesn't decrease the temperature because it's isothermal, but it does decrease the volume in that case, all right? And also will adjust the pressure as well, will actually increase your pressure. All right. And so next up is the adiabatic compression, all right, which is still Q is equal to 0, all right, but we notice right here that that we have an adjustment in temperature, right? In this particular case, temperature will actually increase on this cycle here. And then we go ahead and go back to kind of our starting spot, all right? So the main thing here, and we'll see the entire process all together here, all right? We see this changing, this piston basically just going up and down, all right? And that is an engine. If we can get mechanical work out of the system based upon differences in processes, thermal processes, well then we have mechanical work being produced, all right? All right, first things first. We look at the Carnot cycle, starting with A to B. We said isothermal expansion. We put a hot energy reservoir on the bottom of this, which essentially allows QH to go into the system, all right? This will expand, which essentially means that its work is being done to go ahead and raise the piston, all right? The temperature is staying exactly the same, so the volume is increasing on us, all right? So volume increases. I think you can imagine the pressure is decreasing on us in this case. And you could always go back to PV is equal to nRT, right? Temperature stays exactly the same, stays constant. Well, P goes up, volume has to go down, and vice versa. Volume increases, but pressure will decrease. So pressure is going down in this case. All right, next up. What we have here is the adiabatic expansion from going from B to C pictures, basically. And when we take a look at that, we could say, all right, well, Q is equal to 0, all right? That's what we know from adiabatic. But you notice right here, it's all insulated. Okay, so if it's all insulated, there's no hot energy reservoir going on right there. So what's going on in this particular case, the gas is doing work as well, right? It's essentially increasing. Okay, so the piston is raising in this case, the gas is doing work. In this process, all right, we have to kind of keep in mind that, we have to still understand that everything is changing on us basically, right? Pressure, volume, and temperature, they're all changing on us. Okay, so even though no heat is entering or leaving, we still see the temperature actually falling. All right, temperature falls from a higher temperature to a colder temperature. Okay. Keep on going here. This is the third process here. We go ahead and change out the energy reservoir to a cold energy reservoir. All right, and in this particular case, this is called isothermal compression. We do see that the temperature got to that cold temperature, but it stays exactly there from the previous slide. All right, so it's compression, the volume's going down, the temperature stays exactly the same. All right, volume goes down, but that means the pressure is going up, pressure is increasing on us. All right, and in the fourth picture here, we have back to adiabatic compression. All right, the temperature does increase on us from TC to TH. Right, and you notice once again we have that insulating kind of brick right here, which allows no heat exchange with the surroundings. Right, Q is equal to 0. That's adiabatic in that case. Okay, so the volume changes, the pressure changes, and also the temperature is changing. Temperature is actually increasing on us. Okay, so the work done on the gas, right? You can understand the gas is doing negative work because we have this compression going on, right? So overall, you have this cycle, right? So we start at A. Let's think about this once again. You start at A, right? And this is the isothermal, right? Go to A, go to B. A to B, that's isothermal. So maybe I'll take a little. A to B. I'll just say isothermal, all right? And so in that case, you saw that QH got added to the system. This is where it was in contact with a hot reservoir. All right, from B to C, this is adiabatic. All right, which means Q is equal to 0. There's no change of Q in this case, right? Q is equal to 0 from B to C. But we did go from TH to TC. We decreased temperature there, all right? From C to D, this is going back to isothermal, all right? So isothermal, no change in temperature, but you notice that heat energy is being lost to the cold reservoir that it's touching, okay? So that's interesting. And then we have from D back to A, all right? This is once again adiabatic, all right? And this is where we go from TC to the higher temperature, back to the higher temperature right there. All right, so the entire work of this process is right here in the cycle. It's in the area enclosed. It is the area enclosed, I should say. All right, and don't forget, we always have QH minus the QC is equal to that work, all right, of the engine. Okay, so the difference between the QH and the QC, that is the net work that we have, the area enclosed by the curve. All right? And don't forget, the internal energy of the system, and the reason we are able to say this is because the internal energy of the system, the change of that, was equal to 0. All right? Because this is a cycle. Okay, back to exactly where we started, spot A. All right, I highly advise you to take a look at the active figures that are on your content management system to go ahead and see how things change. You can adjust some variables, but you do see this process in action, and it kind of gets you a better depiction of how this process actually goes. All right, so as you can imagine, we'd probably want to talk about the efficiency of the Carnot engine, even though we said it's not going to be 100, but it's going to be the upper limit. So what actually is it going to be? The efficiency can always be defined we've already discussed this. For any engine, for any heat engine, I should say, efficiency is the work that the engine outputs divided by the hot heat, the QH that you actually put into the system. All right, and it could also be 1 minus QC over QH, as we've seen from a previous slide. But Carnot said that the upper limit, right, is just going to be replacing the QC and the QH with TC and TH, right? Because those were directly related to the QC and the QH that we were referring to. If you look on the previous slide right here, we know that TH and QH are related to each other. TC, QC, in that process from A to B, there is a direct relationship between the two. So that's a nice, easy expression that the efficiency of a Carnot engine is 1 minus TC over TH. All right. And so we can go ahead and say that's the efficiency of a Carnot engine. All right. Another thing to keep in mind is that these temperatures, you always have to use kelvins. All right. Don't forget about that. Don't use Celsius. Okay. And then Carnot engines operating between the same two temperatures will have the exact same efficiency, as we could see from our equation. All right, some notes about this. If the temperatures, the high and low temperatures are exactly the same, then we know that the efficiency of the Carnot engine is exactly 0. All right. If we had TC, if we could have TC equal to 0 Kelvin, which we've never been able to achieve, well then the efficiency is going to be 100%. Right? That just kind of tells us, once again, that we can't have 100% efficiency for any engine. Okay, so no reservoirs are available that are that cold. Right? Efficiency is always less than 100%. But we could use this to manipulate the efficiency a little bit, right? Because if we can decrease TC as much as possible and increase TH, then we get a better efficiency. All right. Now, obviously, that will take energy to change anything from your surrounding environment. So, typically, TC is going to be around room temperature, 300 Kelvin. So, basically, you put money or time and effort into getting TH as high as possible, and that will make a more efficient engine. All right. A Carnot cycle heat engine can also run in reverse. All right, this would be the best heat pump that we have available. All right, so instead of efficiency, we could talk about COP. All right, the COP for a given combination of hot and cold reservoirs, all right, that would be the highest maximum possible COP that we can possibly get. And real quickly, instead of using Qs, we can go ahead and convert to temperature. All right, so for the Carnot heat pump, all right, in heating mode, this should be an H, sorry about that. All right, in heating mode, we could say that the COP is the hot temperature, all right, the high temperature divided by the difference in the temperature from hot to cold, right? Because we can understand we're trying to get as high of a temperature as possible because we're heating things up. In the cooling mode, very simple, TC is on top, difference between the temperatures is on the bottom because in cooling mode, we're trying to extract as much cold energy as possible, or the cooler energy, I should say. All right, so COP is limited, typically below 10 for more practical applications. All right, so let's go ahead and take a look at the Carnot cycle in action using the steam engine example. Okay, so for this example, we have a steam engine that has a boiler that operates at a certain temperature. All right, so we have 500 Kelvin. All right, and the energy from the burning fuel changes water to steam, and this steam then drives the piston. The cold reservoir's temperature is that of the outside air. So we have 500 here and we have 300 here. All right, so we know what our cold temperature is, we know what our hot temperature is. What is the maximum thermal efficiency of this steam engine? And the key word here is maximum. All right, as what's been stated before, Carnot cycle, the Carnot cycle, is the maximum efficiency you could possibly get for any particular system. All right, and so knowing efficiency for an engine of the Carnot cycle, efficiency for Carnot is 1 minus Tc divided by Th. All right, so now it becomes really easy. 1 minus the cold temperature is 300, hot is 500, all right, and you get 0.4, which obviously is equal to 40%, right? And that would be the maximum thermal efficiency that you could possibly get knowing these two temperatures, the hot temperature and cold temperature of the reservoirs, hot reservoir and the cold reservoir. All right, let's go to the gasoline engine. All right, now the gasoline engine, you're just kind of talking about how the gasoline engine actually does what it does. All right, there's a 6-process system, all right, that occurs during just one cycle of the gasoline engine here. All right, so for a given cycle, the piston, as we know in an engine, will go ahead and move up and down. Actually, it'll do that twice. All right, it's what we call a 4-stroke cycle, but we're still looking at 6 different processes on our pressure versus volume graph, right? And so the cycle we're actually going to look at is what we call the Otto cycle, all right? And we're going to see how it's going to work in just a little bit. So here's the Otto cycle, which might remind you of the Carnot cycle, but they're different things, all right? You see on top and on the bottom, there are adiabatic processes, which obviously is different than what we saw for the Carnot, because Carnot was isothermal, adiabatic, isothermal again, and then adiabatic again. All right, so this was A, this was B, this was C, and this was D. All right, that was the Carnot cycle. This is the Otto cycle, which you notice on top. So this, let me go back here. Carnot cycle, adiabatic. Oops, sorry about that. That's isothermal. And this was adiabatic. This was isothermal. And this was adiabatic right here, okay? So for the Otto cycle, you see adiabatic on the top and on the bottom, but on the sides, you see the volume staying the same. So that would be isovolumetric for this and isovolumetric for this right here, all right? Now, so you can see for the adiabatic, obviously Q does not enter or leave for the adiabatic process from C to D. And really we should be starting at O and then go into A. So let's do that. So we go from O, so it's a certain volume, and we just increase the volume from O to A, all right? And that's, as you know, it's a constant pressure process to go ahead and do that. And then from A to B, you see an adiabatic process means Q does not enter or leave from A to B, but the temperature did change. From B to C, you see an isovolumetric process, pressure increased, and we had QH enter the system, right? Which is, you know, typical of any engine. This is where we get all of our QH from, all right? And then from C to D is adiabatic once again. We dropped temperature. We decreased in pressure, all right? There's no Q that got lost or gained, all right? So pressure, temperature, and volume all change. From D to A, you see isovolumetric, volume stays exactly the same, pressure decreases, temperature decreases as well, but you see QC being expelled at that instant, okay? So you see this whole engine process, you know that the work right in here, okay, is going to be based upon the QH, the subtraction between QH and QC, to go ahead and help us figure out our overall efficiency of this process. All right. So it's another cycle, not as efficient as the Carnot, but still something that we use on a regular basis for gasoline engine aspects. All right, this closely models what happens in a piston environment when we're using a spark plug to go ahead and burn some fuel. And this process, we cannot call it reversible. This is an irreversible process. So it goes through one cycle, and then essentially what we have to do is start over from the origin or from O, right, and then do the process again. Okay, it's because basically we're not taking the exhaust and using it again, basically. So that would, you know, if we were able to do that, use all that exhaust and use it again somehow, that would be a reversible process there. Okay. So we just kind of just do the process over in that case. So there's also an active figure on this. I would advise you to take a look at so you can get a better view of all the things that I'm referring to here. All right, let's actually go a little bit further into this. This is the conventional gasoline engine, which, you know, you can also look at the Otto cycle for that and see all the different processes that are going on here. All right, so let's look at these guys individually. All right, but you do notice, just kind of a quick overview, a piston is moving up and down. All right, but this all has to work in sync. So basically, we have this little plug here that opens up to allow fuel and air, the right mixture, to go ahead and enter the piston chamber. All right, that closes back up. The plug closes right here. All right, and we notice that the piston actually went down to go ahead and allow the air and fuel to enter. All right, but the piston is now moving back up in this case to go ahead and really increase the pressure on that air and fuel mixture. At that exact instant, when it's moving at its highest point, we notice that the spark plug fires, right? And that essentially combusts the fuel, all right, which gives the piston a big force moving downwards, all right? So I think you could see that the temperature is going to change at this instant, all right? You know, it's a very quick process right there, right? And then we have this this higher temperature gas that is exerting a force on the piston, all right? And once that force essentially is expended, then we want to go ahead and exhaust all that gas to go ahead and do this process over again, all right? So we open up this plug to allow the exhaust to leave, which essentially pushes all the gas, because the piston is going to go up to push all the gas out, all right? And then it's going to go ahead and rotate again to go ahead and allow this process to happen again. All right, so we use this up and down piston to go ahead and draw in the air and also to expel the air as well. All right, so let's look at the different strokes that we're talking about here. All right, we have the intake stroke. All right, and this is where we essentially are increasing the volume. If you look at the Otto cycle, this is where we go from O to A, because we're increasing the volume, the piston's going down, the volume's increasing right there while maintaining the same pressure. And it's the same pressure because it's open to essentially the environment, or let's just say the inner workings of the engine. It's all, you know, the same pressure there. So we're not changing pressure at all. Okay, so it draws it in. All right, next up, we go from A to B. Now A to B was an adiabatic process, which means that, okay, well, if we go from A to B, if you remember, A was here and B was somewhere here, all right, you notice that the volume decreased. Oops, this should be a P, pressure. All right, so the volume decreased, the pressure increased. And what's going on there is that the piston is just pressurizing the system, volume's decreasing, pressure's going up, but there is no loss of Q. All right, so you can imagine this process either happens really quickly, which is the process, because this is a really quick process, or you could do it by nicely insulating everything. But this is because this goes really quickly in the system. There's no loss of Q, or gain of Q, I should say. So that's going from A to B. And then next up, all right, we have the this is not ISO, this is the isovolumetric. Sorry about that. All right, so we went from A to B adiabatically, all right, then we go straight up to point C. All right, so volume, pressure, volume right there. So for the isothermal process from B to C, all right, what's going on here is we are increasing the pressure significantly, because what we're doing is lighting this thing on fire, basically, putting a little spark in there, increases the temperature and increases the pressure. Okay, so we're at a new higher temperature and we're at a new higher pressure as well. All right, so then we go, the next one from C to D is going to be adiabatic. All right, and adiabatic, we didn't lose any heat because this has happened really quick. We didn't lose our gain. But we did notice that the volume increases because we went from point C to point D. All right, the volume decreased, the pressure decreases. As you notice, the piston is now moving down in this case. So that's the C to D aspect. All right. And then when we go from D down to A, that's just going straight down. All right, that's an isovolumetric process. All right. And so we do see the temperature decreases, the pressure decreases as well. Okay, so pressure drops suddenly, volume is approximately constant in this case, no work is done, all right, and what we want to go ahead and do is go to the last thing here is from A to O. This is where we actually expel everything, right? So we can decrease. So here's point A, here's point O over here, all right? Volume, pressure, once again, we're going from A to O. We decrease pressure, right? We're decreasing volume, pressure staying exactly the same because it's open to the environment here, right? And this is where we actually expel the gas, all right? And then we're ready to go ahead and start this process over again. All right, the Otto cycle has a certain efficiency. It's not the Carnot efficiency that we would like to say, right, for any engine, but it is a certain efficiency that has to actually do with the Molar specific heat. All right, so you see 1 minus 1 over the V1 minus V2 ratio to the gamma minus 1 power. Gamma is the ratio of the Molar specific heats. Right? If you remember, gamma was Cp divided by Cv, the higher one's on top, the lower one's on the bottom. All right. So that was what gamma was if you have forgotten. All right. And then V1 over V2 is just the compression ratio, right? We have the initial volume compared to the final volume in that particular case. We have a compression aspect. All right. Now, so let's take a look at where this equation actually came from, and you'll notice that the derivation is not easy, but it's not that difficult, but it does come from somewhere. So let's go ahead and take a look at that derivation. Okay, so we're going to go ahead and derive the thermal efficiency of the Otto cycle. We're going to imagine this is an idealized Otto cycle, right? And we're going to treat the working substance as an ideal gas. So here's a picture of the Otto cycle in terms of all the different processes that happen to go from A all the way back to A. All right, from A to B, we should notice it's an adiabatic process, which means for any adiabatic process, we have Q is equal to 0. All right, to go from B to C, it's a constant volume process. All right, and this is where we have heat entering the engine, entering the system. From C to D, all right, we have another adiabatic process that still means Q is equal to 0, but as we notice, we reduce in temperature. All right, and then from D to A, constant volume process with another reduction in temperature, and we see an exhaust heat that has left, that's QC. All right, that heat has left the engine as an exhaust. All right, so for any efficiency equation, we need QC and QH. We need to get some equation or represent that in the things that are given to us in terms of the ideal gas. So let's think about, we're going from B to C, all right? And I want to find QH. Don't forget, we're going to take the absolute value, all right? So if I want QH, this is a constant volume process, NCV, right? Number of moles times the molar specific heat times the change in temperature. And don't forget, we're going to keep everything positive, so in this case, TC is bigger, and then we're going to subtract TB, all right, to give us a positive overall change, but we know that we would have done that in the same, no matter what, because it would be final minus initial, all right? And so that's representation of QH, and then let's do D to A, because that's where QC comes into play, all right? We're going to do absolute value of QC, which is equal to number of moles times same CV, but the change in temperature is going to be TD minus TA, all right? And obviously this is initial minus final, but since we have the absolute value, we're going to do the biggest minus the smallest, all right? Okay, so we plug this into the efficiency of any engine, which is 1 minus QC over QH, and using absolute values for these. All right, and so when I go ahead and plug everything in, we have 1 minus, we're going to put QC on top, so that's really the TD minus TA on top, TC minus TB is going to be on the bottom, and the N, obviously the N, the CVs will cancel out. So QC on the top, which is going to be TD minus TA divided by TC minus TB. Alright, so we have this expression here, and we can go a little bit further. Alright, we should remember we have an expression or a relationship for adiabatic processes, alright, that say, alright, well, T times volume to the gamma minus 1 power is equal to a constant. Alright, if that's true, that means that I know that TA, the temperature at position A, times the volume of A at position A to the gamma minus 1 power is equal to the B situation, alright? Because we're only talking about adiabatic processes here, not the constant volume processes that we were referring to really over here, alright? So if for adiabatic process going from A to B, alright, then I could say, alright, well, this is TB VB gamma minus 1. And I could also do the same thing for the other adiabatic process C to D, that TCVC gamma minus 1 is equal to TDVD gamma minus 1. All right. Okay. So going a step further here, if we kind of do a little partition here, and we take this equation, and I get TA all by itself. TA is equal to TB, but we see VB on top, VA on the bottom, and they're both, or the ratio is to the gamma minus 1 power. Right? And we can keep on going here. Right? We could say that we have initial volume and a final volume. All right. So just make this, put into a format that we noticed for the equation of the efficiency for an idealized Otto cycle. It has V final volume and initial volume. All right. I'm going to put in terms of V2 and V1 that we see here. All right. So VB is the same thing as V2. VA is the same thing as V1. So we can go ahead and put those right there. All right. And if I go ahead and do the same thing for this expression, this equation, all right, I get an expression for, let's say, TD in this case. If I get TD all by itself, all right, TD all by itself, that leaves TC, VC on top, VD on the bottom, and I have that to the gamma minus 1. So that equals TC, VC, as we see right here, is V2 is on top, divided by V1, and that's to the gamma minus 1 power. All right. Okay, so if we take these two expressions, this one and this guy right here, and we subtract them, all right? So what does that mean? Well, I take TD and I subtract TA, all right? And so, not a big deal. We can go ahead and subtract them very easily, all right? And so we should notice that we can go ahead and say, all right, TD minus TA is going to equal, all right, TC V2 over V1 gamma minus 1 minus TB V2 over V1 gamma minus 1. All right. So I'm going to take the V2 over V1 gamma minus 1 out of each of these guys. So we're left with TD minus TA over TC minus TB is equal to V2 over V1 gamma minus 1. All right. All right, and so we see TD minus TA, TC minus TB is the same thing as what we have right here. All right, so we're pretty much done. Efficiency is equal to 1 minus V2 over V1 to the gamma minus 1 power. And that is the efficiency of the Otto cycle right there. All right, so we just derived that expression. All right, took a little bit of work, but it really goes back to what kind of processes do we have to go from A to B to C, C to D, and then back to A. All right, so it's kind of putting a lid on Otto cycle here. We have typical compression ratios of around 8 for the Otto cycle. All right, so we can understand, V1 over V2. Right, V1 is 8 times as large as V2. Okay, so that would be the compression ratio that we're typically referring to right there. All right, and gamma is about 1.4 for the gases that we're actually using. Remember, we mainly talked about monatomic gases, but we can most definitely for gasoline, it's a complex molecule that we're talking about. And the efficiency is 56%. If we this is just an ideal Otto cycle. All right. Now, real engines are about 15 to 20%. That's because there's a lot of things going on, typically like friction, energy transfer by conduction. You're not insulating it, and it's not completely insulated. Incomplete combustion of the air-fuel mixture. We're not combusting everything, so we're not getting as much energy out of the system as we get, or as we want. All right, but with the advances in automobile technology, these efficiencies are most definitely going to go up. All right, and just a word about diesel engines, which have been in the news related back to Volkswagen. All right, but they're still more efficient than gasoline engines. Using diesel fuel are still more efficient because they don't use a spark plug. Right? Spark plugs obviously uses energy to go ahead and operate. It's because diesel fuel, we can compress diesel engines actually compress the fuel at a much higher ratio. All right, and so if that's going on, that compression is so big, then you could actually raise the temperatures high enough to go ahead and ignite the mixture without a spark plug. All right, so that's why diesel engines can save a lot of fuel and a lot of energy overall, is because you don't have to create a spark. All right, so that's why they're more efficient than gasoline engines, because they can ignite without a spark plug. All right, last topic I want to cover is entropy. All right, and this is kind of a new topic for physics overall. It has to do with statistical mechanics. All right, but it's really related back to still the second law of thermodynamics, but it's what we call a state variable. All right, that we haven't really introduced just yet. All right, but the reason that we talk about entropy is because isolated systems, all right, they have a tendency. They tend towards something as opposed to something else. All right, and there's many examples of this, and we don't have to go really into all the different examples, but you can imagine that, when you throw a pack of cards out of the box, in the air, it tends towards going everywhere, basically, right? As opposed to just staying in, all stacked up, right? And obviously there's a possibility that it can be all stacked up when it lands on the ground, but the statistical law of averages tells you that they're going to be all over the place, right? So we can actually try to quantify that using entropy, all right? Isolated systems, they tend towards disorder, all right? And entropy tries to measure that disorder. It's kind of a interesting topic that you can most definitely go further into in the textbook and also outside resources, but it's going into this, really it defines why the universe is expanding, all right? And what's going on with the universe, right? Why are we tending towards this as opposed to condensing, if you will. Okay. All right, so how do we kind of start this discussion here? Well, it's about really microstates. Right? Microstates is just one configuration. So imagine, once again, throwing the pack of cards onto the ground, and you have one configuration of those cards. Throw another pack, and you have a different configuration. Those would be two different microstates, right, of all those constituents of the system. Now, a macrostate is a description of the conditions from a macroscopic point of view. Just basically says that the macrostate would just be cards on the ground. All right, so related to things that we've been talking about, it could be what's the pressure of a system, what's the density of a system, what's the temperature. But we know that that's related back to where are all the atoms in a particular gas, right? If this is a gas, we have molecules of atoms at different locations. So those molecules can be in different locations, but we could still have the same pressure. They have the same density, but those molecules can be in different locations. We could have a temperature for the system for two different microstates that are exactly the same. The temperature is exactly the same, but we know those molecules are in different locations. All right, so that would be these pressure, density, and temperature would be macroscopic. Okay, so for a given macrostate, all right, we already said that a number of microstates are going to be possible. All right, and then all microstates are going to be equally probable. All right, we just know that any microstate is going to has the same chance of happening. Okay, but when you look at all these macrostates, right, it's found that macrostates associated with disorder, right, have far more microstates than those associated with order. All right, so disorder just kind of tells you that there's just a lot more things can possibly happen when things are more disordered. When you have more things that are ordered, you don't have as many opportunities for differences, basically. All right, as many combinations, if you will. All right. So when we think about probabilities, the probability of a system moving in time from an ordered macrostate to a disordered macrostate is far greater than the probability of the reverse. All right, so there's more microstates in a disordered macrostate. Just like we said before, it's just going to be very difficult for, or not difficult, but the probability that a macrostate goes from disorder to order is going to be very low. Okay, and that's mainly because microstates, once again, in a macrostate, a disordered macrostate, there's a lot more possibilities. All right. So kind of just said in a different way, if we consider the system and its surroundings to include the universe, right? A system and its surroundings includes the universe is always moving towards a macrostate corresponding to greater disorder. All right. So once again, entropy is a measure of that disorder. Right? The entropy of the universe increases in all real processes. Right? When you heat things up, even when you cool something down, you're actually taking heat from some other place to go ahead and transfer it to, you're taking heat out of that system and depositing that heat typically into the environment, into the universe. All right. So in all real processes, the entropy of the universe actually will increase. All right. So this is another statement of the second law of thermodynamics. Basically, this is the underpinning feature of the second law of thermodynamics. All right, so entropy and heat. All right, the original formulation of entropy dealt with the transfer of energy by heat in a reversible process. All right, so basically, you know what reversible means. We start at one spot and we go to another spot. All right, and we can go in one direction or we can go in the other direction from initial to final. All right, this once again is always on the volume pressure situation, pressure graph. All right, so if we can imagine that dQr is the amount of energy transferred by heat when the system follows a reversible path. All right, so we can imagine that either Q goes into the system, right? I believe this is a big arrow, sorry about that. All right, or Q can leave the system, but it's just the amount of energy transferred by heat when a system follows a reversible path. All right, so we can go ahead and define a change of entropy as that energy transfer divided by the temperature at which that energy was transferred at. All right. Now that's a little bit easier said than done because sometimes this temperature does change when energy is being transferred, and we have ways to deal with that. Okay, so the change in entropy depends only on the endpoints and is independent of the actual path followed. All right, so to make it a little bit, just kind of say it in a different way, is that entropy change for an irreversible process can be determined by calculating the change in entropy for a reversible process that connects the same initial and final points. Basically, all we're saying is, since all I need to know is how to get from I to F, all right, well, I can call that an irreversible process. Right? I'm just going in one direction. Right? And if I go from F to I, that could still be irreversible, but I don't have to follow the same path. I can go on this way, basically. All right? And since we're saying that entropy only depends on the endpoints, then it doesn't matter if these guys are reversible or irreversible. Right? So it makes things a lot easier for us when we're really quantifying things. All right, so dQr is measured along a reversible path, all right, even if the system may have followed a irreversible path. All right, so once again, it just doesn't matter. Reversible, irreversible, let's not even worry too much about it. All right, but the meaningful quantity is really the change in entropy, not what entropy is at one instant. It's what's the change from one spot to another spot. So this could be ice melting, right? There's a change there. It could be ice getting colder, right? That's a change. Okay, so what's the change of entropy for that process? And that's the important. It's not what is the entropy of this block of ice. That's not really the important thing. We want to know what's the change. All right, so for a finite process, all we need to do is integrate. All right, if I integrate both sides of that previous equation from initial condition to a final condition of entropy, all right, I get a change of entropy. All right, and that's equal to the integral of initial to final of the dQr divided by temperature. Okay, so, if this is, let's say that this is a piece of ice that's changing temperature. Well, the Q, is MCAT, right? And really, it should be MC dt, then we're going to divide it by temperature, as you notice, and then we take the integral in that case. All right, and you're probably going to get a natural log when you go ahead and take that integral. All right. If this was just a piece of ice changing to a liquid, right? Well, then that would be the mass of the ice times the latent heat of fusion, all right? And then divided by the divided by the temperature at which it's going to happen, right? Well, temperature M and LF, they're all constant, so they could just come to the outside, and that essentially would be your change in entropy. And we have an example of this that I'll show you right after the next slide here. All right. So the change in entropy of a system going from one state to another has the same value for all paths connecting the two states. So once again, trying to make things easier for you from initial to final. All right. All we need to know is what's the two ends. Okay. The finite change in entropy depends only on the properties of initial and final equilibrium states, as we just said. So that just means we can choose whatever path we want. All right. Just as long as the initial and final states are going to be exactly the same. If we're talking about a cycle, all right, for any system under process that is a cycle, then that means the overall change in entropy, that's what this circle means, it's a cycle. Overall change in entropy is going to be 0, all right? So integrating, the integral is over a closed path, that's what that symbol means, right? But if it's a cycle, because it comes back to exactly where it is, then the change of entropy is exactly 0. All right. All right, so just to end things, let's go ahead and just look at a quick example, which I kind of referred to earlier, a couple slides ago, but it's exactly pretty much the same thing. Let's take a look at the change in entropy of something that's going to go ahead and melt. Okay, for this example, we have a solid that has a latent heat of fusion, LF. It's going to melt at a temperature of Tm. All right, all we want to do is calculate the change of entropy of the substance when the mass of this substance is going to go ahead and melt. All right, so we got to keep in mind whose entropy are we looking at. This is the entropy of the substance. All right, so I think you can imagine that if the entropy what is the entropy going to be, positive or negative? Well, when a substance melts, we can understand energy is being added to the system, and that means that the entropy is going to increase of that system. So we should expect a positive in this case. So when we say delta S, change of entropy, is equal to the integral dq divided by temperature. That's the general equation for a change of entropy. For this process, temperature stays exactly the same, so that's 1 over t, bring it outside the integral, and integrate dq. Right? And so when we integrate dq, we just know we have q divided by temperature. All right? For this process, heat is going to be added to the system, heat energy added to the system to melt. So we know q for anything that melts is going to be the mass of the object times a latent heat of fusion. All right? And we divide that by temperature. All right? So this is how we really deal with changes of entropy. We have to understand what is the process that's happening in this case. And we have to most definitely take a look at what substance is having the entropy changed. Sometimes we could even say the entropy of the universe, right? If heat is actually being released into the universe, then we know the entropy of the universe is actually increasing. In this case, we're just looking at the entropy of the substance, which we know heat is being added to that substance, right? And its entropy is actually increasing.